Welcome to Data Dude Library. In today's video, we're going to talk about the first order linear differential equations. A linear differential equation has a form of a of x times dy dx plus b of x times some y is equal to c of x. Now, a, b, and c could be functions of x, but they could also be constants. In order to get this to some form that we can work with, we're going to divide everything by a of x. That would give us dy dx plus, we're going to call some function b over a, some other function called p of x times y is equal to some other function f of x, which is just the division of c and a. From here we can derive something called an integrating factor, which we will call mu of x, which is equal to e to the integral of p of x dx. Notice that this p of x is the same as the p of x that stands in front of y. To solve these kinds of linear differential equations, we're going to take integrating factor and multiply both sides by this integrating factor. Once you multiply and simplify, you get the following formula. Keep in mind that mu is our integrating factor, which formula was mu of x is equal to e to the integral of p of x dx. Let's try an example. Example 1, dy dx minus 3y is equal to 0. So in this example, notice that negative 3 is my p of x, and 0 is my f of x, which is going to come in handy very soon. The first thing you want to do is find the integrating factor. So mu of x is equal to e to the integral of p of x, which in this case is negative 3 dx. So as you know, e integral of negative 3 with respect to x would just be negative 3x. Normally we would put a constant in there, but we're not going to do that in this case because the constant will come in later on with the formula. So now that we have mu, we can go ahead and plug it into our original formula. Y is equal to 1 over mu of x, which in this case is e to the negative 3x, integral of mu to the x again, which is e to the negative 3x, times f of x, which notice in our case was 0, dx, plus some constant c. Simplifying from here, 1 over e to the negative 3x would just simply give me e to the positive 3x. And notice this part right here is multiplied by 0, which ultimately becomes 0, and we have this multiplied by c. So my final answer would just be c e to the 3x. Next few examples, I encourage you to press pause before I solve this problem with you, just so you can get an idea of where you are with this topic. This example is going to be very similar to the other example, one minor difference, which is it's not going to equal to 0, it's going to equal to 6. Keep in mind the integrating factor is mu of x is equal to e to the integral of p of x dx. Hopefully you press pause and had enough time to take a look at this example. So the first thing you want to do is identify your p of x and your f of x. So again, the p of x in this example will be the same as previous, where it is the number that stands in front of y. The difference is that it's no longer a 0. It is now a 6 as my function of f of x. So to find the integrating factor, I'm going to find e to the integral of p of x, which is negative 3 dx, which again is the same as the previous example, which was e to the negative 3x, and that is my integrating factor. Now that I have that, I'm going to plug that into my formula. Y is equal to 1 over mu, which again was e to the negative 3x, integral of e to the negative 3x, which is my mu again, times the function f of x, which in this case is 6 dx plus some constant c. Now we have y is equal to 1 over e to the negative 3x, which will simplify momentarily, times, I'm going to take the 6 outside of the integral, and it's an integral of e to the negative 3x dx plus c, and now we're going to integrate. So we have e to the positive 3x, which again is just bringing that negative power up to the top, times 6, an integral of e to the negative 3x is simply e to the negative 3x divided by negative 3, and then plus c. Notice 6 and 3 will reduce to 1. So what we have is e to the 3x times negative 2 e to the negative 3x plus c. Now I'm going to distribute this e to the 3x through my parenthesis, and notice that e to the 3x and e to the negative 3x will just cancel, leaving me with negative 2 plus c times e to the 3x. Once again, I encourage you to pause the video in this example, just so you can have a minute to take a look at it and solve it. So the first thing you have to do here is divide both sides by x, or divide everything by x. All right, that way I have my derivative dy dx all by itself. And that will give me that p function in terms of x is equal to x to the 5th power e to the x. Now notice I have my p of x here, which is now a function of x. This right here is my function f of x. Before we move on though, we need to find our integrating factor, which is mu of x is equal to e to the integral of p of x dx, which is e to the integral of negative 4 over x dx. I'm going to take that negative 4 and bring it outside of the integral, which is negative 4 integral of 1 over x dx, which is just natural log of x. Now, with properties of natural logs, or logarithms, period, we can take this negative 4 and bring it up as a power. So this would just simplify to e to the ln of x to the negative 4th power, and we can now cancel this e and ln, if you will, and have x to the negative 4th power as my mu. Now that we found our mu, we can go ahead and plug it back into our formula. Y is equal to 1 over mu of x, which is x to the negative fourth power, times the integral of x to the negative fourth power times f of x, which from above you can see was x to the fifth power e to the x dx plus c. From here we can just go ahead and simplify, so we have y is equal to x to the fourth. Again, I'm going to bring the negative power up to the top, making it positive, times x to the negative fourth times x to the fifth will give me x to the first power, so integral of x to the first power e to the x dx plus c is the simplified version of what we had. From here, in order to integrate this, we need to remember integration by parts. If you recall, the formula for integration by parts was fg prime is equal to fg minus integral of f prime g. So in our example here, we have integral of x e to the x dx, with x being my f and e to the x being my g prime. So the way I like to write this out is f prime and then g and g prime, and fill in what I know. So f is x and g prime is e to the x. So derivative of x will just be 1, and integral of e to the x would just be e to the x. And now I'm going to go ahead and plug it into this formula, which is f, which is x, times g, which is e to the x, minus integral of f prime, which notice is 1, I'm not going to write that, times g, which again is e to the x dx. So just simplifying this a little further, x e to the x minus integral of e to the x, which is just e to the x, plus some constant c. And now I'm going to take out e to the x because that's what's in common. So e to the x is in common. I'm going to take that out. I have x minus 1, and then plus c left over here. But since I have this c and this c, there's some arbitrary constants. I'm just going to make it some other c. Now I'm going to take what I found and substitute it back in. So y is equal to x to the fourth times, instead of the integral, I now have e to the x times x minus 1. And then again, plus some arbitrary constant c, which I'm just going to combine the red c and the green c here into one of them. And then it's just a little simplification here. I can distribute, giving me y is equal to x to the fourth e to the x times x minus 1 plus x to the fourth c. And you can again distribute through this parenthesis, kind of make it look a little better. And giving us x to the fifth e to the x minus x to the fourth e to the x plus cx to the fourth. And that's what we have here. I have one more example for you guys. Again, press pause and try it on your own. I hope you pause this video again. So the first thing we have to do here is divide everything by x squared minus 9. Giving us dy dx plus x over x squared minus 9 times y is equal to 0. Notice this function of x is my p of x. And the 0 again is going to be f of x, which as you saw in our first example, it's going to make it nice and easy for us there at the end. But we need to get there first. So mu of x is e integral to the integral of x over x squared minus 9 dx. So in order to find this integral, we need to use substitution. So in this integral, we're going to let u equal to x squared minus 9, and therefore du would just be 2x dx. Notice our original integral does not have 2x. If it did, we would be ready to just substitute in, but it doesn't have it, so we need to put that in there. We can't just put a constant in there, we have to balance it out. So I'm going to put the 1/2 in front of the integral, that way it all balances that out, and we are able to find the integral. So we have 1/2 times the integral of 2x and dx, notice become du. So that becomes du. All I have left is 1 over x squared minus 9 is my u. So 1 over u du. So we have 1/2 integral of 1 over u is nothing more than ln of u. And we know what u is going backwards here. So it's 1/2 natural log of x squared minus 9. Now remember, this is just the top part of that integral. So we still have to take that to the e, or e to that power. Now again, with logarithms, we can take this 1/2, put that as a exponent here. We have e to the ln of x squared minus 9 to the 1/2 power. And 1/2 power is nothing more than a square root, and e and ln will cancel each other out for lack of better words, and our mu, therefore, of x becomes square root of x squared minus 9. So taking this back and putting it back into the formula from the beginning, we have y is equal to 1 over mu, which is 1 over square root of x squared minus 9, times integral of mu, again, which is square root of x squared minus 9, times f of x, and I mentioned this in the beginning of this example, and f of x is just 0 dx plus c, right? Which again, that 0 is going to make this whole entire thing 0, giving us our final answer of c over square root of x squared minus 9. I hope you found this video helpful. Please like and subscribe to the channel for more, and I'll see you soon.